I'm Minh, and I'm working with Emilio on the recursive construction of the multiple control Toffoli, right? So before we start, let me reintroduce the concept of the Toffoli gate and the multiple control Toffoli gate. So the Toffoli gate is a control NOT with two controls, and it has a NOT acting on the target bit, right? So the simplest case of a Toffoli gate is actually a CNOT gate, which has one control bit and one target bit, right? And the action of the CNOT gate on a 2-qubit state A and B is A tensor A XOR B, right? Where A is the control and B is the target, right? So we can generalize this to n qubits, right? N control bits, and we would call this the CNX gate, right? So this matrix of the CNX gate is actually defined as the diagonal as a diagonal matrix with ones on the diagonal entries, and for the last two elements, we actually have ones on the anti-diagonal entries. And as we can see here, this represents the X matrix, right? Because we know that when all the control bits in the multiple control Toffoli gate is 1, right? We would flip whatever the input is for the target bit. So this is what we have. And what we are interested in is the relative phase multiple control Toffoli, right? So the way to define this is to first define what a relative phase error is. So given unitary matrix U, its relative phase counterpart is defined as V such that every element of V is equals to U up to a relative phase factor. So in this way, we can define the relative phase multiple control Toffoli as P, C, and X. And we define this as Z0, Z1 up to Z 2 to the power of n plus 1 minus 3 on the diagonal entry. And for the last two elements, we have, again, two relative phase, but it's in the anti-diagonal entry, right? And again, Zj is E to the I theta j, where theta j can be different for each column of the matrix. So with that in mind, we get into the known techniques on the problem. And I think researching the literature around this problem, I think that there hasn't been a lot of research into this, and that's why we're really interested in it, because it has a lot of potential in applications. Because the reason why we're interested in the relative phase gate is because its implementation cost, whether it's CNOT cost or T cost, is lower than that of the normal Toffoli gate. So we have Dmitry Maslov, who does the construction of n equals 2 and n equals 3. And we also have Craig Gidney, who came up with a 9n plus a constant factor construction for the relative phase. So our construction is a recursive one. So obviously we need to have base case, right? So our base case is n equals 2 and n equals 3. And this is what n equals 2 looks like. This is a Toffoli modulo a phase shift, right? So as you can see, we have CX gates on A and B here. That's to control these qubits, right? And we have one target here. So we call this a PC2X gate. And again, this is a PC3X gate. And you can see that these CX gates are controlling these ABC qubits here. And these constructions, we got them from Maslov, from his paper, which outlined how to build these gates. So we can generalize that further, right? So this is what we came up with during our work. So we look at these base case construction, particularly PC3X, right? We look at them and we see how can we generalize them to more control bits, right? So one thing we can do is we can take any two CNOT gate that is acting on the same control bit, and when we can extend that to a Toffoli gate acting on another bit, right? And then, so here's an example, right? We see that this bit here, which is acting on the A qubit, right? So these two gates, and we can extend them to a Toffoli gate, and then we can replace them with a phase gate, right? A phase Toffoli gate. And this will give you a PC4X, which is a multiple control Toffoli with 4 control bits and a phase different for depending on what your input is. So to build like arbitrary relative phase CNX where n is bigger than 3, right? So you first extend the CX of the A qubit, so this, you extend that to C, ceiling of n over 3 of x, right? The B qubit to C, n over 3, and that's the floor of x. And the last one is of the control of qubit C. You extend this to this bad boy over here, and that's just the how many ever control you have left from these ceilings and floor. And we repeat that process until we decompose all the gates up to that base case. So that's how we build the gates use recursively. And so to talk about when we talk about the cost here, we're considering the CX cost, right? So that's the 2 qubit entangler gate cost. And the best way to demonstrate the cost is to look at like a table of its value. And we're actually interested in the asymptotic growth of this technique here, right? So we will be looking at, let's say, what we're interested in is the second difference, right? We look at the second difference, we can see that as n increase, right, the second difference, the change in the second difference occurs less and less often, right? So we can summarize this and we can express this in a mathematical ways by saying that the average second difference at n, right? We can express that and we take the limit as n approaches infinity and we get 0. So what does this tell us? This tells us that our function, the implementation cost, it grows subquadratically asymptotically. And to apply these gates, it actually has less application than the normal phaseless implementation. But Emilio is going to walk you through one of the applications because I think it's still really important and it will offer a lot of speed up in this respect. So take it away, Emilio.
Yeah, thank you. So yeah, as Minh said, we know that the cost is less, so now we need to find an application. So yeah, so first of all, by Maslow, we know that we can write our CNX gate as a product of a phase diagonal and the phaseless Toffoli. So this just means that the D matrix adds the phase that comes with the phase implementation of a Toffoli gate. And again, Dn is just a diagonal, so basically a relative alternative of the identity matrix. And we know that the phase CNX is a unitary matrix, so its inverse is its conjugate transpose. And this is important because next slide, please. Okay, so since we know that its inverse, it's the conjugate, we know that this gate is also a relative phase CNX with the phase that it is applied inverse. So it is again defined as a diagonal with the x gate with the relative phase x gate at the end. And this can be written as in equation 6, which is an CNX gate without any Toffoli, and the phase with the conjugate transpose of the original phase of the gate. And to construct this like in a real circuit, we just take all the gates from the original phase CNX, we reverse them, and we take the inverse of all those gates. And in taking the inverse, the CNOTs and the Hadamard gates stay the same. So we only need to inverse the T gates, which are the only one that are not their own inverse. So yeah, now that we know how to construct the conjugate transpose, which is its inverse, we propose this application, which is basically the same as doing a normal CNOT or control unitary with one ancilla qubit, which will be the Y register. And as you can see, it first applies the phase CNX on the X register. It uses the Y register as an ancilla to store the result of that CNOT. And then we apply the unitary based on the Y register on the T register. And the last inverse of the phase CNX reverses the gate, the phase that was applied by the first one. So basically at the end, it's just like replacing the CNOTs because we don't get any phase effect. And we have like outline a proof for this here. So as you can see, this first equation is basically what the circuit applies to the registers. So first we have the phase CNX and tensor identity, because in the first gate, the T register doesn't have any effect. So yeah, so applying the first one just in the Y register applies the same as a normal CNX, is Y plus the product of Xi, which is the and applies the DN, which is the phase gate, to the X register. So then we apply the identity tensor control U operation. So identity on X and control U on Y and T. So that just uses the product from the first CNOT and applies it to the T register. So this is the final product. And yeah, the phase still stays the same. So now when we go to the last gate, we see, yeah, so now for the last gate, can you change next one? Okay, so now for the last one, we're gonna take the base case of Y equals the 0 ket, just for simplicity. And doing that, we first simplified the equation in the first line, which is just the and times ft. So if the and is 1, we get the effect of u on t, and if it's 0, we get the effect of t. And on the second register, we just have, again, the CNOT of the first CNOT we applied. And when we apply the inverse of the first CNOT, we see that the effect on the second register is reversed because it's like taking two ANDs. And the important thing is that we apply two phases which are inverse of each other in the first register. So since these two phases are inverse of each other, they cancel out, they give us the identity. And at the end, we just have X register unchanged, the second register also unchanged, which in this case is ket 0. And in the last register, we have the effect of control U of the unitary gate based on the values of the first register. So that's basically the application we're proposing for these phase CNOT gates. And this application can be generalized to more to another unitary gate that acts on the three registers with some restrictions, but that's a little bit longer to explain. So we just decided to expose this application for this particular talk. And I think that's everything for today. So thank you. And if there are any questions, you can go ahead and tell us.
Thank you, Emilio. Thank you, Minh, for that talk. If there are any questions from the audience, please feel free to unmute yourself or share your questions in the chat.
Yeah, I have a question. So I think you mentioned that the construction is sub-quadratic in the number of T gates. Is that or sub-quadratic in the number of CNOT gates?
Yes.
So, for instance, a Craig-Gidney's trick to apply like an AND, so like a temporary AND to a thing, which you're also sort of using, but like you're computing the thing, applying it to some other qubit and incomputing. When does your method give better T counts than just using Craig-Gidney's trick, using just regular Toffoli's or stacked regular Toffoli's?
Oh, so you're talking when my method is better than Craig's in terms of CX count?
Yeah.
So it's better than Craig-Gidney's count for n less than 28.
Less than 28, and bigger than his method becomes better.
Yeah, but yeah.
Okay.
Bigger than his method is better.
Okay. It's pretty cool.
Are there any more questions for our speakers? Okay, maybe I can ask a small one, and this just for my clarification. So on slide 20, you said the second difference. That's I think I missed that part, but could you explain that again? Yeah, the average second difference over here.
Okay, so if we look at the second difference column here, right, we see that the second difference is non-zero, right, at some point, right, but not at other values, right. So if we actually look at the longer table, we actually generate like 400 values, which is actually not necessary because it's only better for like the first 27 cases, right? But we look at this and we see that the second difference is non-zero once in a while, and the distance between these non-zero values gets larger and larger as n increase, right? So let's say, so the second difference value, right? these can be modeled by 2 to the n, but the distance between them is 3 to the n, right? So if we take the average second difference, which is the non-zeros divided by the distance between them, we get like the average second difference. That's how we're defining it, right? And as n increase, 2 to the n over 3 to the n equals 0, right? It's a geometric sequence, I think.
Got it. Thanks.
And since it's like the second difference is equals to 0, then it's subquadratic.
Yeah. All right. Thank you.